Okay. So the next topic that we're going to kind of jump into. So we've looked at confidence intervals, right? And really what we've been doing is trying to figure out where that population mean is or where that population proportion is. We're using our sample to then build this range of values where we said we know with certain levels of confidence that the true population mean or population proportion is in this range. Okay? So we're going to push it a little bit further with hypothesis testing. Okay? So we still are kind of coming from this point where we don't know where this population mean or population proportion is. I'll probably talk about this mostly in the context of the mean today, but everything would apply to the population proportion as well. So we don't know where this population mean's at. So we're going to develop a hypothesis about what the value is. Right? So we might say, you know, I'm going to assume that this population mean is, I don't know, equal to 40,000. Right? So we'll have these things called null and alternative hypothesis, right? So we'll kind of go through and explain a little bit more about these in a second, but basically the null hypothesis is what we're going to assume to be true. Okay? The alternative hypothesis is what I'll make sure I say this carefully. So the alternative hypothesis is going to be basically the complement of the null hypothesis. So if we're assuming this is true, the null hypothesis is true, the alternative hypothesis is, well, if we can find enough evidence that goes against that assumption or supports the alternative hypothesis, then potentially we can say, okay, whatever we assume to be true isn't true, right? For example, if I think that the average income in the US is 50,000, I take a sample of 100 people and I see a sample mean of 90,000, well, what I assume to be true probably isn't true, right? Because it'd be very unlikely that if the true mean was 50,000, that thing that I assumed it was, that value I assumed it was, it'd be very unlikely that I see in my sample mean a value of 90,000, right? It's very far away from that true mean. And I know if 50,000 is the true mean, my sample mean should be normally distributed around it. And I could figure out, well, how likely or unlikely, if that value of 50,000 is true, how likely or unlikely was it that I did see a sample mean of 90,000? And that's kind of the setup. So if we have a sufficient enough evidence that goes against, you know, whatever we assume to be true, we can reject the null hypothesis. If we don't have enough evidence, we'd fail to reject it. So let's say I assume that that average income is 50,000. I take a sample and I see 53,000. Well, yeah, that's different than what I assume to be true. It's different than that 50,000 value, but it's not that far away, and we know that the sample means will be normally distributed around that true population mean. So we could see values kind of slightly to the left or the right, right? And that wouldn't be very unlikely, even if the true mean was 50,000. Okay? So I have this kind of other example where we can think about, maybe I want to think about what's the average kind of mass market beer's ABV, right, or alcohol by volume. So I know that kind of this, I selected one specific beer. I know that it has kind of this ABV of 7%. Okay? So I want to know, okay, does the average mass market beer have an alcohol by volume that's lower than 7%? Right? I think that's probably, you know, could be true. Okay? So I take a sample, 36 different types of, you know, brands of beer, and I find that kind of 4.5% is the average. So how can I kind of turn this into a null and alternative hypothesis, right? Well, my null hypothesis is going to be the assumed true state of nature. So whenever I want to try to find something, whatever I'm trying to test for, I'm going to assume the opposite is true, okay? So here I'm wanting to see, does the average mass market beer have a ABV lower than 7%? So I'm going to assume the exact opposite and like stack the deck against myself. Right? So I'm going to assume that the opposite is true or that it's greater than 7%. And then the alternative would be the exact opposite of that, right? I said earlier it's the complement. Okay? So it's basically everything that would contradict the null or the complement of the null. Okay? So if you want to think about kind of what we're going to be doing, and I think I might end up drawing something here and coming back to this slide, but there's basically three scenarios, right? So I have this assumed true value, right? I make this assumption in the null hypothesis. If I find evidence that goes against it, right? So let's say I assume that that average ABV was greater than 7%, and I see a sample mean of, I don't know, I think what was it, 4.5, did I say? Yeah, 4.5. Well, that goes against that assumption pretty hard, right? Pretty strong. So in that case, I found evidence that went against my null, inconsistent with that null hypothesis, which we'll write as H subscript 0. Right? So if I find evidence that goes against it, I can reject the null. Right? If I assumed it was greater than 7%, but my sample mean is 4.5, well, that goes against the null, and I'm going to reject it. The other two scenarios are we find something that is consistent with the null, right? If I assume that the average ABV was greater than 7%, and I found a sample mean of 7.5, well, that supports that null hypothesis. It supports that assumption that I made. So I'm not going to reject the null, right? Or fail to reject the null. We could find evidence that's inconsistent, but not inconsistent enough. So let's say I assume that that average ABV is greater than 7%, and I see a sample mean of 6.8. Well, that goes against the null, right? That's 6.8 is not greater than 7%, but it's not very far away. And if the true kind of average ABV was 7%, it's pretty likely that from a sample mean, I see a value of 6.8. Right? That's not very far from that value of 7%. So we can find evidence that goes against our null and goes against it strong enough that we can reject. We can find evidence that goes against it, but it's not strong enough to reject it, so we would fail to reject. Or I find evidence that is consistent or supports the null, in which case, well, I'm not going to reject it, right? I'm going to not fail to reject. So those are three kind of scenarios we're thinking about. I think I'm going to skip this for now. Well, yeah. What I'm going to do here is, I think, jump ahead a little bit in terms of the slides, but I think it gives us a little bit more of a context for what we're going to do. So we're waiting, there we go. So let's start out with that kind of assumption where we're thinking about, if I'm looking at the distribution of my sample means, right, and I've assumed that that true population mean is 7% or greater. Okay? So let's just assume for a second that, if I had a null hypothesis, which was that the true mean, I'm going to assume it's greater than or equal to 7%. Okay? So I'm going to just take kind of the lowest value in that range. Right? I'm going to take that 7% value and use that as my assumed true mean. So a lot of times the way we'll write this is my assumed true mean of mu subscript 0 to kind of identify it's that mean coming from the null hypothesis. We're going to assume it's 7%. So under that assumption, if this in fact is true, my sample mean should be normally distributed around that value. Right? We know that sample means are normally distributed around the population mean. Well, I can't see the population mean here, but I've assumed it's a certain value. Right? So we're going to go off the assumption that that is in fact true. Okay? Well, if I saw something that, let's say I take a sample and I see a sample mean of 7.5. Well, that supports the null, right? That the true mean, in fact, is 7 or something higher. So I'm going to fail to reject the null, right? This is evidence that would support the null. Okay? My alternative hypothesis is going to be, I said, the complement of my null, which would just be that that true mean is, in fact, less than 7%. Right? So basically the complement here, right? We can go back to some early things that we've talked about. So now, if I see a sample mean, let's say of 4.5, well, how many standard deviations away from that assumed true mean is 4.5? Well, I could figure that out. As long as here we'll start out with an example where, let's assume somehow we know the population mean, population variance. Okay? If I did know the population variance, I could look at my sample size. I think it was 36, if we go back to the example. I could figure out this standard deviation, I could turn that value into a z-score, right? So we would just take, usually we would subtract the mean and divide by the standard deviation of my sample means. Well, here now, when I subtract the mean, I'd be subtracting that assumed true mean. Right? Once I have my z-score, I can find how likely or unlikely was it that I saw 4.5, right? What's the probability that I see 4.5 or something less if this assumed true mean is in fact the true mean? And if this probability gets low enough, right? Like let's say I find that probability, and if this was the true mean, the probability I saw 4.5 as a sample mean is like 0.001. Well, that seems pretty unlikely, right? That I would see that sample mean, right? The probability is 0.001 if this was in fact the true population mean. So I'm okay saying, well, look, this was so unlikely for me to see this as a sample mean that this probably isn't the true mean, right? It's probably that the true mean is somewhere down here, right? So if the true mean was somewhere down here, well now 4.5 would be a lot more likely of a value for me to see, right? The probability I see 4.5 or something below that would be a lot more likely if what I assumed was wrong, right? And that the true mean is actually a little bit lower. So that's kind of the idea of what we're thinking about. Because we know something about this distribution of sample means, we can find the probability that we saw certain values for our sample mean under whatever we've assumed to be true. So that's kind of where we're going, right? And I'll probably draw a couple more things like that, but I just want to kind of give a little bit of a context, right? So I've already identified kind of some null and alternative hypothesis here. And the way I wrote this, actually, let me pull this up real quick. Right, H subscript 0 is my null, and H subscript A we'll call the alternative hypothesis. Okay. So kind of try to relate this to some non-numerical example, just to give a little bit better of a kind of understanding of what we're doing. We think about the null hypothesis is what we're assuming to be true, and the null is we're stacking the deck against ourselves, right? Whatever we wanted to find, we assumed the opposite was true. Okay? So if we think about like a court case, what's the whole point of a court case? They're trying to determine whether or not you committed the crime. They're trying to provide evidence that shows you're guilty. Right? So what do we do in terms of the court case? We assume the opposite is true, right? Hopefully you are assumed innocent, right, until proven guilty. Right? So we start out, right, trying to find whether or not this person's guilty. So the null hypothesis will be, we'll assume they're innocent, right? And if we can find enough evidence that goes against that null, then we can reject it, right? If I'm assuming you're true, you know, or if I'm assuming you're innocent, that you didn't commit maybe say a murder, but they find your DNA at the scene of the crime, right? You don't have an alibi, you had some motivation. You know, if they have enough evidence that goes against that null, they can reject it, right? So the alternative is that you're guilty. We assume that you're innocent as the null. We find enough evidence that goes against the null. We reject that null. So we reject that you're innocent and kind of send you to jail, right? We found enough evidence that we could rule out that assumed true value, the null hypothesis that you were innocent. We can rule that out and you go to jail, right? Well, what if there's not a lot of evidence, right? So, you know, maybe you don't have an alibi, but you know, there's nothing linking you to the crime. There's no motivation. Well, we don't have enough evidence to go against that null, so you remain assumed innocent, right? And you kind of go free. So this is kind of the idea. We're trying to relate this to kind of a court case example, non-numerical here. This is the idea of what we're doing with this null and alternative hypothesis. Okay. Any questions up to this point? I know this is a lot. We'll spend quite a bit of time on this here. One thing I'll mention too, before I forget. Oh, sorry. Saw some confused looks. You guys got to let me know if I sometimes forget to switch that over. So everything I just said in words, I was walking through kind of this slide, right? So we've got kind of, we assume that someone's innocent. If we find enough evidence that goes against that, you go to jail. Not enough evidence, you remain assumed innocent. But it doesn't really matter this slide there. It's kind of what I was saying, and we're just kind of the idea of trying to get across. So one thing I want to make sure I don't forget to say. So I think on the syllabus, we're supposed to have an exam at the end of this week. That's not obviously going to happen. We've got probably another week of lectures I want to get through to kind of explain hypothesis testing. So next week, I'll have a little bit more details about when the exact date of that exam is going to be, but it is kind of coming up here in the next week, week and a half, okay? All right, so I already mentioned this, but right, here's how we're going to write our null hypothesis, H subscript 0. Here's our alternative, H subscript A. So we have three different types of hypothesis tests that we're going to do. Okay? I kind of walked you through one, or at least I showed you an example of one, where we had kind of assumed that it's greater than or equal to a certain value, and then the alternative was the opposite of that, which was that it was less than that value. Okay? But we have two other tests. So one of them would be, we call a greater than test, and we have a less than test. So the way that we refer to these, or the way that they're named, is based off of the alternative hypothesis. So if I have a greater than test, it's because there's a greater than sign in the alternative hypothesis. If I have a less than test, I have a less than sign in the alternative hypothesis. Now, really what we're doing here is we want to see whether or not the true mean is above a certain value. Remember, this mu subscript 0, we're eventually going to have an assumed true value that we're plugging in there. So in practice, this ends up being a number, right? We assume that, or sorry, in this example, what do? We said we assume that the true mean is greater than or equal to 7, right? So that's a less than test, because what we're really trying to do is to find evidence that goes against that, right? It goes against the null and actually supports the alternative, which is what we had here, right? We found 4.5, which goes against the assumed true value that it's greater than or equal to 7. So we've got that greater than and less than test kind of named after the sign we see in the alternative hypothesis. Another way we'll refer to these tests is greater than, less than, right tail, and left tail, okay? And that kind of makes sense because notice in this one, this was the example I kind of had set up here. Our alternative hypothesis was that the mean was less than 7%. So only seeing sample means on the left side of the distribution would be values that go against the null. So less than or left-tailed test, and then the opposite, we would kind of have a greater than or right-tailed test. There, only values that would go against the null would be as if we see values that support the alternative, which would be that it's greater than a certain value. So that's kind of how we name those tests. And then the third is going to be, we have this not equal to test, right? So maybe, this one's a little bit harder because now I'm not just assuming like, well, is it greater than or less than a certain value? Now I'm assuming it's one specific value, right? That the mean is equal to maybe say 7% in the example that I had before. So it's equal to exactly one value. So the alternative there, well, what's the complement, would be that it's not equal to that it's any other value than what I assumed it to be. So those are our three types of tests. We'll refer to the greater than and less than test as one-sided, right? Only one side matters there, right? So if you think about when I find this sample mean, if it's above the assumed true value, or it supports this alternative hypothesis here, right, only values that are above what I assume to be true would support the alternative, right? So it's only one side matters. Okay? This might make a little more sense when we work through kind of that first example. And then here, well, if I've assumed that maybe say it's equal to 7%, well there, if I see evidence on the right or the left side, it goes against that value, right? If I assume that it's 7% and I see a sample mean of 8.5 or I see a sample mean of 5.5, both those values go against that assumption, right? So there we call that kind of a two-sided test. Okay? And the way in which we do these hypothesis tests will change a little bit depending on if it's a one or a two-sided test. Okay? So that's kind of our setup here. We've got three different types of tests we can start to think about. Any questions on this before we keep moving? Okay. So what are our steps going to be? All right, so first, are we talking about a mean or a proportion, right? We can identify what population parameter we're looking at. Determine whether it's a one or two-sided test, right? So it's kind of write out your null and alternative hypothesis and figure out Do I have a one or two-tailed test? Do I have a right or a left-tailed or greater than or less than? It's kind of the next step. And then we have to make sure we're including a sign of equality somewhere. Now, this in practice isn't going to be something that's really going to trip us up, because what we're going to always do is put the equality in the null hypothesis. You don't necessarily have to. Once we start working through examples, I'll explain like why you could put it in the alternative hypothesis here. Notice the equality sign is always in the null hypothesis. Well, if instead I would have accidentally, put it in the alternative, it doesn't matter because we're dealing with a normal distribution. The probability of any one value should be 0. But the normal convention is that we include that equality sign in the null hypothesis here. And the two-sided test kind of reminds you of that because it is just the equal sign, right? It is just the equality sign. Okay? So those are kind of what you have to make sure we're doing. Right? So if we go back to this example and think a little bit more about it, right? What would our null and alternative hypothesis be? Well, if I want to test for whether or not the average mass market beer has a lower ABV than 7%, that's what I wanted to test for. So another way that we'll say this is the alternative hypothesis is what you want to test for. Okay? That's what I'm trying to prove. So I assume the opposite is true, which is that it's greater than or equal to 7%. Right? And that was kind of what we had written down on the dot when I was using the dot cam earlier, right? We assume that it was greater than or equal to 7. The alternative then would be that it's less than that. And now we can start to think about how can I actually determine whether or not I reject or fail to reject, right? What value would be far enough away from 7 that I could reject that as the true mean, right? 4.5 seems pretty far, but what about 6.2? What about 5.9? Like where's the cutoff? Okay. Just to kind of give another example though, kind of constructing these null and alternative, because you can imagine if the type of test matters, is it a left-tailed, right-tailed, two-tailed test? Well, we have to make sure we can identify the null and alternative hypothesis well then. So let's say that an economist wants to establish the mean retirement age is different than 67. So someone tells you the mean retirement age is 67, you don't think that's correct, you think that it's something other than that, right? Well, if I want to test for whether or not it's different than 67, what I'm really saying is it's not equal to 67. It's some other value, but it's not equal to 67. So our alternative hypothesis is going to be that it's not equal to 67. So what do? We assume the opposite is true, and the null hypothesis becomes that that true mean is equal to 67. Right? So even though I don't think it's equal to that value, I'm going to assume that it is and kind of stack the deck against myself. Okay? Here I want to point out, anytime you kind of see these, these problems that we're working through, these word problems, anytime you see with the word different or different than, right, you're probably thinking about a two-tailed test, right? Is it different than, or is it not equal to this certain value? And that's going to be your alternative hypothesis. So then the null, you just assume that it is equal to that value. So the two-tailed tests, in terms of identifying them, I think are a little bit easier. You're really looking for that phrase of different than. We could go through, I think for the sake of time today, I think I'll revisit this either at the end of class or kind of going back to the next class. So we'll save this. Let's go to I want to kind of conduct one of these tests so we can get a look at it today. So I was kind of saying, what evidence would be inconsistent enough that I can reject the null? 4.5 is pretty far from 7, but what about 6.3? Right? So how am I going to determine this? Well, once we have that assumed true value, first thing we need is, do we have evidence that contradicts it, right? If I see 7.5, well, that supports the null. Then, okay, I'm done. I don't even have to go through any more steps. I found evidence that supports the null. I'm not going to reject the null, right? That's easy. Well, what if I see 4.5? Does that go against what I assume to be true enough? Okay. Well, the methods that we have to kind of determine this, I can get this minimized, are the p-value and critical value approach. So the one that I'll kind of introduce today is the p-value approach. Okay. But we'll kind of revisit next week the critical value approach. Remember, we're not going to have class on this Friday. okay, to kind of keep my sections kind of in the same location because of the study day this week. So you guys get a study day, I guess, for this class this week. So we're going to use that same example, right, where we have a what type of tailed test here. So another way that you might see this, and the reason why I write this is because in your Connect homework, or if you're looking at the Learn Smart, a lot of more stats books kind of use H subscript 1 here as the alternative. To me, why we don't have to use numbers? I can use the letter A and it makes a lot more sense, right? But you will see this, so I wanted to make sure I bring that up. So if I look at my alternative hypothesis here, I have a less than sign. So I've got a one-sided test, and it's a left-tailed or a less than test, okay? Because I look at the alternative hypothesis to determine that. So if in fact what I assume to be true, right, this null hypothesis, if that in fact was true, what would the distribution look like? And that's where I kind of already jumped the gun and I said, well, look, if we're assuming this is true, I'm just going to use the lowest value in this range, right? Because if I can reject 7% as the true mean, well, then I can for sure reject 8%, right? Because if 4.5 as my sample mean is inconsistent enough with this assumed true value, well, then if it was 8%, it would just shift that distribution to the right and make the probability I see 4.5 even less likely, right? So all I have to do is test for that kind of, in this case, lowest value in that range, right? So this blue kind of distribution we draw earlier, we said that, well, look, if this is the assumed true mean, I know that the sample means will be normally distributed around it as long as I have a sample size over 30, which I do here, right? So make sure that central limit theorem is met. Right? So, you know, I kind of already, like I said, I jumped the gun on this one, but I wanted to make sure we got through an example. So I saved some things, you know. We could see 4.5, 6.7, 8.5. Well, 8.5 is an easy one. That supports the null, so of course I'm not going to reject the null. 4.5 and 6.7, well, they go against the null, right? They're less than 7%, so they don't support the null hypothesis here. But, you know, do they go against it enough? 6.7 is pretty close to 7, 4.5. Well, yeah, it is kind of far away. But if I had a really large standard deviation on this distribution, it may not be that many standard deviations away, right? It may not have a very large z-score. Okay? So if I don't have a large z-score, you know, if you think about, if I turn this into a z-score and it ends up being like, I don't know, -0.2, well, that's not very, that's 0.2 standard deviations below the mean. That's not very far. You know, so I have to take in consideration the standard deviation of this distribution as well. So we'll use that sample mean value of 4.5. We'll do the test for that one value, and then we could think about what would change if I wanted to test some of these other values. Right? So we've got 4.5%, right? That goes against my null. What I can do is I can kind of create, I said earlier, I'll turn that 4.5% into a z value, which will now, because we're kind of using that z value to perform this hypothesis test, we'll kind of refer to it as a z statistic. Okay? The kind of broader category is test statistic. You can kind of think about, we've got like this broad category of test statistic, and we can break this down, right? When we use a standard normal distribution, we can call this a z statistic. And you can already imagine, because of things we've done with confidence intervals, there may be scenarios where I need to use the student t distribution, in which case I would be calling this kind of a t statistic, right? So this is really just identifying what distribution it's coming from, but both of them will be kind of considered test statistics, right? So here, we're going to start out today with examples where I said we assume, or we start out with examples where we have this population variance. So we're going to be calculating z statistics, right? We know the population variance, similar to confidence intervals. We then know, okay, these sample means, once we kind of convert them into my test statistic, they should be coming from a standard normal distribution. All right, that time I didn't have to switch it over. So it's going to be really similar to what we've been doing. right? This shouldn't look that much different than when we were calculating z values before for sample means. I take my sample mean value I'm interested in, so that would be my 4.5%. I subtract the assumed true mean, right? Because I don't know the true population mean now, but I have an assumed true value. Okay. So here that would be our 7%. And then this denominator just represents what? Do you recall what this represents? Standard deviation, but there's a standard deviation kind of variance in there. So it's the standard deviation of my sample means, right? The statistic I'm looking at, this denominator represents the standard deviation of that statistic. So the standard deviation of my sample means. Okay. So kind of similar as to before with confidence intervals, what you really could think about is I can calculate this intermediate value first and then plug it in, or I could just do it all at one time, right, and do something like that. Right? So very similar to confidence intervals, where we could do the intermediate kind of step or not. Okay. All right, where are we at? Okay, perfect. All right, so, oh, sorry. My scroll wheel just went crazy. Okay. So when we want to use this p-value approach to figure out, is the sample mean I saw inconsistent enough with the null hypothesis that I can reject it? Well, it's going to be a little bit different for different types of tests. This will probably make a little more sense as we work through some more examples. But you kind of imagine, right? If I'm looking at this left-tailed test or less than test, I want to find, once I turn this into a z-score, I want the probability of seeing that value or anything below it, right, to the left. So my p-value is essentially going to be the probability of seeing this sample mean or anything below it if this in fact was the true population mean. Okay. Now for a right-tailed test, the only evidence that's going to go against, for a right-tailed test, we would have basically right tail or greater than test. Well, now the only thing that goes against the null is things that are on the right-hand side. So there, once I find a value and I turn it into a z-score, there I'm looking at the area to the right, which is why the way that we kind of write what the p-value is going to look a little bit different. But I think this will make, this is just like the mathematical way to write it. I think this will make a little more sense when we work through some examples, what the differences are between these different types of tests. Okay. So I want to give a slightly, I've got some kind of formal definitions of what the p-value is here. But let's think about, let's clean this up so we can get a little bit better of a definition. I think that will make more sense to us, right? So let's say I've got my sample mean, and I've assumed that that value of 7% is true. Right? I see 4.5, and here was the assumed true value. Right? So I'm thinking about what I want to find what my p-value is it's the probability that I saw something this far away from the assumed true mean or anything further, right? Or said differently, I know I can convert this value into a z statistic or my test statistic. Once I have that z value, I can go to the standard normal table, look it up, and it will tell me the area to the left. Or the probability that I saw something this many standard deviations away, right? Because that's what a z value represents, the number of standard deviations away from the assumed true mean. Okay? So before it was the number of standard deviations away from the population mean. We don't have the population mean now, but we have an assumed true value. So the p-value is the probability that I saw something this many standard deviations away, or in this case below the assumed true mean, or anything even further away, right? Anything more standard deviations below that. So that's what my p-value represents. Okay? So if my p-value is a probability, first of all, what does it have to be between? This probability has to be between 0 and 1. Yeah. Right? So that kind of helps me at least think about the p-value. Now, this was the scenario we had. We could easily start plugging our values in, right? The only thing that I would need here is, at this point, I haven't told you what the original population variance was. And I think I have that in the slide, which I'll kind of return to in just a second. So here's my p-value for this left-tailed test, right? Because we started out kind of with our alternative hypothesis was that it was less than 7%. So we'll come back here in a second. It's frozen. There we go. We'll return to this slide in 1 second. I want to kind of work through this example. Okay. So here's going to be my steps, right? I determine the null and alternative hypothesis. The other thing that we need is to specify an alpha. Okay. So I haven't talked about this quite yet, but we'll kind of come back to this. This is going to be basically, okay, once I find my p-value, right, and I know the probability I saw something this many standard deviations away or further, right, how low is, at what probability am I okay rejecting the null? Okay. Then, we can calculate our z-statistic. We already talked about that. Once I have my z-statistic, that's how I find that p-value. Now, the last step is I compare that p-value to alpha. So what alpha is going to be is kind of like the threshold for anything that has a probability below this. I'm okay rejecting the null hypothesis, right? So let's say I return to this example and I find the probability of seeing 4.5 or anything lower, if in fact the true mean was 7 here, maybe I find that probability is like 0.03, right? So there was like a 3% chance that I saw this as my sample mean, if in fact this is the true mean. What I assumed to be true was true. Well, that seems like a pretty low probability, right? So at the very beginning, before I even calculate my z-statistic and find the p-value, what I'm going to do is set alpha, right? I might set alpha to say, I don't know, 0.05. So what that's saying is if I find the p-value is less than 0.05, I'm okay rejecting this as this assumption, right? I'm okay rejecting my null hypothesis because anything that's 5% or lower, anything that's less likely than 5%, I'm okay with saying, well, look, it was so unlikely that this can't be the true mean. It's probably more that like the true mean is somewhere down here, okay? So I'm gonna set that threshold. This is something I choose, alpha, right? Now you can kind of think about with confidence intervals, we start to, it's kind of similar idea with alpha here. If I'm setting alpha at 0.05, we can start to think about this is gonna correspond to a 95% confidence level. So I'm rejecting with 95% confidence if my p-value is less than this cutoff alpha that I set. So the rejection decision will be if my p-value is less than alpha, which is really saying the probability that I saw the sample mean that I did or anything further from that assumed true mean, if the probability of seeing that is anything less than 5%, or anything, the probability is anything less than 0.05, then it's so unlikely that I'm okay rejecting this as the true mean, because it probably isn't, right? If it was a true mean, I would have been seeing values like 6.3 or 7.2 or something like that, right? So I'm okay rejecting it if the p-value is less than whatever that alpha I set. Okay? That's kind of the general idea of the p-value approach. Okay? Any questions up to this point?
So one of the questions on the test, I'm assuming like one of the big ones is going to be involving this as well as creating
Confidence intervals, yep.
Yeah, confidence interval.
Yep, so, and like I said, we're just going to keep going through hypothesis. So I'll go through examples, but I'm also just going to be reiterating and kind of showing you some of the different concepts. So like the exam's not going to be like next Monday, right? So we've got like at least a week and a half. We'll hopefully kind of, all we're going to be doing from here to the exam is probably really just focusing on hypothesis testing. Because in this portion of the course, really everything that we started post, like after the exam, everything's really been building up to like us to be able to do hypothesis testing, right? Talking about the distribution of sample means, right? Talking about the differences between if we have a population variance or a sample variance, right? All these things are going to kind of culminate in doing these hypothesis tests. So all we're going to do from here to the exam is really just focus on this hypothesis testing. Yeah.
And then so the p-value like would be less than alpha in this example. Is that because it's a left field test? Or
Yeah, so that's the next thing that we'll talk about before we end class today, okay? Good question. So the rule of p-value being less than alpha holds no matter what type of test we're looking at, okay? So let's say, what were we on time? Okay, I think this is what we'll do. I'll work through this, we'll revisit this example and go through it completely next class, but that's a good point, and I do want to kind of mention that. So let's say instead we had, I don't know, this is a completely different, but I don't know, we'll say it's, what do I want here? Let's say we had this as our null and alternative, right? So I've got a greater than sign in my alternative hypothesis. So here I've got a greater than or a right-tailed test. Only seeing sample means above 7% would go against the null. So now things like 8.5, right? When I'm thinking about a p-value, it's going to be the probability I saw something this many standard deviations above or anything further, right? Or said differently, I see a sample mean that goes against my null hypothesis this much, or anything that would go against that null hypothesis even more, right? So here for a right-tailed test, my p-value, once I, turn this into a z statistic, well, then I would go to the table. The table tells me the area to the left. I want the area to the right, so I do 1 minus, right? Kind of using some other things we've already talked about, right? So for right-tailed tests, the p-value is the probability you saw the sample mean that you did, or anything greater, or anything to the right, all right? So that's kind of the difference between a left and a right-tailed test. Left-tailed, and that's why I call it left tail instead of less than. Left-tailed test, once you find your z statistic, find the area to the left of it. For a right-tailed test, once you find your z statistic, you're finding the area to the right of it, right? Because we're talking about, really what I'm saying is the probability I saw something that went against the null hypothesis this much, or something that would go against the null hypothesis even more. Well, that's only one direction for a one-tailed test, right? Because if I found something over here, well, that actually supports the null, right? That would be a value less than 7%. So the one-tailed test, I think it's a little bit easier. Like we're using things we've already talked about. Once we calculate that z statistic, it's really just a matter of using that standard normal table to find this area that I want. So the trickier one, and same convention applies, once I find my p-value, I only reject if the p-value is less than alpha. So same rule there, okay? So only reject if that p-value is less than alpha. The trickier one is if I have a two-tailed test. So let's say I'm looking at a sample mean, and we'll actually use those same examples. So let's say we assume that it's 7%, and let's say I see a sample mean of, we'll use that same sample mean of 4.5. But now, I'm assuming that it's equal to 7%, and my alternative would be that it's not equal to that. Right? Well, now if I think about turning this into a z statistic, the probability that I see, remember the p-value is the probability I see something that goes against the null, this as much as my sample mean did, or anything even more. So all these values would be values that go against that null hypothesis or any more. But with a two-tailed test, right, so this was what, 2.5 below? If I saw 9.5, right, well, that's a sample mean value that goes against my null, right? My null now is that it's equal to this value. So seeing something that was this far away from that assumed true mean, well, now I have to think about both directions, right? So now this is the probability I saw the sample mean I did, or anything that went against the null hypothesis more than that. Well, actually, all these values over here would also be sample mean values that would go against that assumed true mean now as well. So now I have essentially two tails, right? So yeah, I can find my test statistic and I can find the area to the left, but I have to remember, it would have been just as likely that I would have seen a sample mean value that went against the null hypothesis on the other side, right? So now, once I find this area, I know that there's an area on the right-hand side that's exactly the same size, right? Symmetric distribution around that mean. So once I find this area, well, if I have a tail on the other side as well, I can think about this is really half my p-value, or p-value over 2, and then half my p-value would be over here. Or once I find the probability I saw this test statistic or anything below it, I could multiply it by 2. Right? Okay. So that's going to be kind of the difference with a two-tailed test. In practice, once I turn, because I'm only seeing one sample mean, to be clear, I'm only seeing 4.5, right? But I know that the probability that I saw 4.5 or anything below it would be the same as a probability I saw 9.5 or anything above it, because this is a symmetric distribution. Okay? So that's why, go back here, for this two-tailed test, once I find that area of seeing that test statistic or anything more extreme, and I say more extreme, right? If it's negative, anything that's a kind of larger negative value. If it's positive, anything that's a larger positive value. For a two-tailed test, once I find that area, I multiply it by 2, because I know that I've got two tails, right? The evidence on either side of my assumed true value, right? If I'm saying it's equal to 7, something on either side could go against that. And then I kind of have a synopsis of what we kind of went through. It's not as detailed per se, but right, left-tailed test, I'll find my test statistic, area to the left, that's my p-value. Right-tailed test, I find my test statistic, area to the right, that's my p-value. Two-tailed test, I'll only see one of these, right? Depends on, the exact example. But once I calculate my z statistic or my test statistic, I'll find the kind of area in the tail of that test statistic. If it's negative, area to the left. If it's positive, area to the right. And then multiply it by 2, because I know I've got two tails there. Okay? All right. So I know this is a lot. Like I said, we are going to be working through lots of examples. I will be discussing it more and giving you kind of different insights into exactly what we're doing with this hypothesis testing. But we should be doing that all of next week, and then I would envision kind of the exam being sometime early the following week. Okay? Yeah. Yep. I'll get some. I'll probably post them. I don't know if I'll get to it today, but probably tomorrow or Friday. I'll even put some practice exams up there. So even if you want to start looking at those, you can. Obviously, we still have a lot of stuff about hypothesis testing to kind of work through. So, all right. We'll see you guys on Monday, okay?